Imagine a world where delicate, porous structures can glide through the near-space environment using nothing but sunlight and the invisible push of photophoretic forces. This groundbreaking research unlocks the secrets behind such phenomena, offering a treasure trove of data, models, and simulations for the curious and the bold. But here's where it gets controversial. Could this technology redefine our approach to atmospheric exploration? Or is it a fleeting scientific novelty? Let's dive in. Access to data and models. This study doesn't just present findings, it hands you the tools to replicate and expand upon them. The photophoretic force models and experimental data are meticulously detailed in the paper and its supplementary information. For the technically inclined, tabulated results from DSMC, Direct Simulation Monte Carlo. Simulations are available on GitHub, while a full breakdown of the simulation methodology is outlined in Reference 8. Source data accompanies the paper, ensuring transparency and collaboration. Think of it as an open invitation to the scientific community to build, question, and innovate. Code and mathematical foundations. Ready to roll up your sleeves? The numerical DSMC and analytic model code resides in the same GitHub repository. All mathematical procedures are laid bare in the methods section, complete with references and supplementary details. This isn't just a paper, it's a blueprint for future experiments. But here's the kicker. How would you tweak the code to test a different material or atmospheric condition? The floor is yours. A library of inspiration. For those hungry for deeper dives, the references section is a goldmine. From Keith's pioneering work on photophoretic levitation for geoengineering to Azadi's solar-powered near-space flight breakthroughs, these studies form the backbone of this research. Did you know that even the Benford brothers proposed microwave-supported aircraft in 2005? And here's a thought. If Cheremison's 2019 paper on non-uniform gas surface interactions is correct, does that mean current models are missing a critical piece of the puzzle? Share your take in the comments. The human side of science. This work was made possible by a mix of institutional support and individual brilliance. Funded by the Starr-Friedman Challenge and the Harvard MRSEC, it's a testament to what happens when curiosity meets resources. The Harvard Grid Accelerator and CNPq Brazil also played pivotal roles. And let's not forget the collaborators, A. Feldhaus, M. Greenberg, and others, whose insights shaped this journey. But here's a question. Should scientific breakthroughs like this be commercialized, as seen with the rarefied technology's patents? Or does that risk stifling open innovation? We'd love to hear your perspective. Visualizing the invisible. The extended data figures bring abstract concepts to life. Imagine slicing through a 2D temperature model to see how microscale ligaments influence heat distribution. Or visualize spectroscopic data revealing how materials absorb and reflect light. These aren't just charts, they're windows into the physics of flight. For instance, Figure 4 compares experimental data with models assuming different NEAC, non-equilibrium accommodation coefficient values. Could these discrepancies hint at undiscovered phenomena? The data is all there. The interpretation is up to you. The road ahead. This research isn't just academic. It hints at practical applications from atmospheric sensors to Mars exploration. The finite element analysis in Figure 6 shows how structures withstand forces, while the patent filings suggest commercial potential. But here's the elephant in the room. Can we scale this technology for real-world use without compromising its delicate balance of physics? And what about the environmental impact of deploying such devices en masse? We're not asking for answers, just sparking a conversation. Your turn to explore. So, what do you think? Is photophoretic flight the future of near-space exploration? Or are we overlooking critical challenges? Could this technology democratize access to the upper atmosphere? Or does it remain a niche curiosity? Drop your thoughts below and let's debate the possibilities together. After all, science thrives on questions as much as answers.